A modern car weighs roughly 4,000 pounds. It is a dense, immovable block of steel and machinery resting heavily on the pavement. Yet, for decades, mechanics have hoisted that entire weight into the air on a single pillar using just a gentle push on a lever. Attempting this with a standard solid tool, like a metal crowbar, would require a lever longer than a football field. It is physically impossible to achieve that kind of leverage within the confines of a garage. This immense lifting power is generated by a trapped liquid. When viscous oil is forced into a high-pressure cylinder, the physics of the system change. Fluids possess a specific physical property that allows them to multiply force, effectively bypassing the biological limits of human strength. For a hydraulic system to function, the fluid must be completely sealed within its container. Any leak causes the entire mechanism to fail. To see why, imagine a horizontal, liquid-filled cylinder. One end has a movable piston, and 3 vertical glass tubes sprout from the top. When you push the piston inward, the liquid rises in all 3 simultaneously, stopping at an identical height. This is Pascal's law. It states that pressure applied to any part of an enclosed fluid is transmitted undiminished and equally in every direction throughout the vessel. Because the pressure never drops as it moves through the container, the trapped liquid transmits applied force to every square inch of the system's interior. A car lift uses an asymmetrical design. Left is a narrow tube with a small piston, area 1. Right is a wider cylinder supporting a large platform, area 2. Applying a downward push to the narrow piston generates our input, force 1. This action creates pressure. In physics, pressure is the amount of force divided by the area it presses against. Following Pascal's law, that exact pressure travels through the liquid, moving across to the wider cylinder without losing any intensity. That pressure now pushes upward against the base of the large platform. Because it encounters a much larger surface area, the total upward push increases. To find this output force, we multiply the pressure by the larger area. Combining these steps gives the master formula for hydraulics. Output force equals input force multiplied by the ratio of the 2 piston areas. This is the physical result of using a liquid to distribute a small effort across a much larger surface. We define this ratio of the 2 areas as the system's mechanical advantage. It tells you exactly how much your initial effort will be magnified. If the area of the lifting platform is 20 times larger than the input piston, the fluid multiplies your force by 20. A 50-pound push becomes a half-ton lift. It might seem like the machine is creating energy from nowhere, but the liquid is simply a conduit. The system takes the pressure from the small piston and spreads it across a wider physical canvas. Because every square inch of that wider surface receives the same pressure, the total collected force is much higher. You are trading distance for power. To move the heavy car up by just 1 inch, you have to pump the small piston down by 20 inches. The energy you put in stays the same, but the resulting force is immense. This same principle is used to stop the car once it's back on the road. Your car's brakes are a high-stakes application of Pascal's law. A gentle tap on the brake pedal sends high-pressure fluid through the car's lines. That pressure pushes against larger pistons at the wheels, which aggressively clamp the brake pads onto the spinning rotors. Because the pressure is transmitted equally, all 4 wheels receive the same braking force at the same time. This ensures the vehicle slows down in a controlled, straight line. From the mechanic's garage to the high-speed highway, trapping and squeezing a simple fluid remains one of our most effective methods for extending the reach of human strength.